also thank you very, very much to Chris and Nick and everyone else for inviting me. What a great event, what a lovely place to be in. Small apologies, by the way. I gave something, well, basically exactly this talk, but perhaps I've proved a few thoughts about a month ago, and one or two of you were in the audience. So if you slope off at the back, I won't feel judged. If it's terribly boring and you've heard it before. All right, so, and to be fair, lots of people in this audience may have heard bits of this before, because what I want to do today is talk about spacetime functionalism, which is a view that I bang on about rather a lot, but then apply it to a putative theory of quantum gravity, non-commutative gravity. So I'm going to outline this kind of spacetime functionalist view, tell you what particular variety of the view I think we should adopt, and then have a little think about how it implies in this particular case. I should also put a kind of big hat tip to Nick Huggett right here, because it was Nick who sent me a paper on non-commutative geometry saying, do you think you should look at this? So this is all thanks to him, or his fault, depending on how you think of it. All right, so I'll give a bit of a prelude before I start that sort of is meant to indicate why I'm interested in this topic and what I think I'm doing. I hope that's helpful, and we'll see if it is. And then I'll tell you why you should all be spacetime functionalists. I'm really committed to the idea that you should all be spacetime functionalists. I'm moderately committed, but not in such a didactic way, to the idea that you should all be inertial frame spacetime functionalists, which is my particular preferred functional definition of spacetime. But you know, the nice thing about functionalism, and I'll say this later on, is you can kind of let 1,000 flowers bloom. It's not like if you decide that something's a functional concept, it's not as if there can't be more than one functional role something plays in a theory. So I'm very committed to spacetime functionalism. I'm moderately committed to the usefulness of inertial frame spacetime functionalism. And I'll try and demonstrate that usefulness by telling you a little bit about non-commutative geometry and non-commutative gravity, and explaining how you might see this kind of spacetime functionalism as playing out in that context. All right, so now for the kind of digression. It's quite unfashionable to talk lots about concepts. It's quite unfashionable in philosophy of physics, perhaps philosophy of science more generally, perhaps even in philosophy. But I think sometimes it's important to get clear on what someone like me takes themselves to be doing. Now, the reason it became really unfashionable to talk about philosophers as doing something like conceptual analysis has to do with, the story we all know about the demise of, logical positivism and the turn that philosophy took in the middle 20th century. And certainly, and even if you sort of bracket some of that context, you can see there's a really worrying role you might think philosophers take, or a role that would just be an obviously bad one for us to take. That is one where we give the necessary and sufficient conditions for the fulfillment of a concept in science. So there's kind of science, and then philosophers come in and we fix the meanings of the terms. That's our useful role, right? And it is a role that people sort of thought about for philosophy at one stage, right? And it's just obviously not a good one, because if you thought that our job was to fix the meanings of concepts once and for all, you wouldn't be taking into account the way that our concepts and our use of words shift around in various ways between theories and between contexts themselves. So if you think about entropy or kinetic energy or force, right? If you tried to define those, say kinetic energy in Newtonian terms as a half mv squared, kinetic energy just disappears in the relativistic context, and that's not what we want to say. So the very fact that our definitions can shift of concepts means that we shouldn't be tied to a kind of sort of austere view of philosophers as providing the analysis of concepts once and for all. But that doesn't mean that we shouldn't talk about concepts, and it doesn't still mean that a lot of what we do isn't conceptual work. There's a lot of good work to be done in tracking and understanding how our concepts change, and in making sure that we're not importing old assumptions into new contexts. So making sure that we understand what's happened to kinetic energy, what's happened to that half mv squared, how it's changed, what associations we can import and which we can't, is an important part of the job of interpreting special relativity. So a reasonable view sees the philosopher not as a conceptual stipulator or judge, but as a conceptual housekeeper. Now, Jeremy Butterfield persuaded me to put these couple of slides in, right? So it's all his fault. I have to blame others. And he said, Eleanor, you should describe yourself as a conceptual housekeeper, a la, Putnam 1962. And I said, Jeremy, no female philosopher of physics can describe themselves as a housekeeper. But then I tried to think of other ways to describe it, and conceptual hygienist was almost as bad. So I've settled for a relatively gender-neutral robot in my image. At least it's not, a sexy maid's outfit. And we'll settle with that. So, but look, when you say what we do is conceptual housekeeping, you might be tempted to kind of see an ellipse there, right? You can all see sort of mirror or just before the conceptual housekeeper bit. And I don't mean that. I think this kind of work is absolutely essential. It might be true that our concepts shift and change, but if we don't bother tracking it and we don't bother trying to identify the way the concepts apply in new theories, the job of interpreting a theory is just hopeless. I mean, in a sense, that the job of going beyond the formalism and saying anything about a theory involves this kind of conceptual tracking. So I don't think that this is sort of trivial or small work. I think it's exactly the kind of thing that we should be doing, and that in fact physicists are doing all the time when they interpret their own theories. Okay, and in particular, these kinds of considerations become really crucial when we want to understand or make progress on new theories. So this kind of new theory, I'm a big one for lazy searching of the internet for probably a copyright violating image when I write a talk. And if you search quantum gravity, this wonderful image comes up. So here you go, guys. This is what we're doing. I mean, it looks so simple, doesn't it? And in particular, it's not just in the context of new theories that I think this is really important. I think the concept of space-time is a really important one to keep track of. One reason for that is that space-time is automatically associated in certain ways with the empirical predictions of a theory. So if you want to know what your measuring instruments are going to do, a lot of those measuring instruments are going to be measuring distances and times. And we tend to make automatic assumptions once we've called something space-time about what it's going to mean for the empirical consequences of a theory. So not keeping track of the space-time concept could lead to bad assumptions being made about the empirical content of a theory, and that would be a pragmatically bad thing. And on a more interpretational note, if you're going to talk about theories of quantum gravity that involve emergent spacetimes or discrete spacetimes, or spacetimes with many more dimensions than 4, then you better be clear what aspects of the spacetime concept you're importing. So this should say something about the kind of potential pluralism behind a project like this. It's not so much that I think you expect to find something that plays exactly the same role as spacetime does in our current theories, in a theory of quantum gravity, but it would be good to understand the role and to understand what aspects of the role are carried forward by some structure in a new theory. Okay, so this is the kind of sloganistic way that I want to try and think about that project, spacetime functionalism. Spacetime is a functionalist concept, functional concept. That is, a field or object is spatiotemporal by virtue of playing a certain kind of role in our theory. So the slogan is, it's spacetime by virtue of what it does, not what it is. So that's the broad view, right? What does that view presuppose? It presupposes that it's a reasonable project to go and look at previous theories, successful theories, theories we think have been helpful, and find some common cluster of roles for spacetime across them. Probably this audience don't need it, but it's also important to say that, contra functionalism in other bits of philosophy, there's no suggestion here that this is kind of a cluster of folk theoretic platitudes or something like that, right? I think that space-time in particular, it's actually slightly different from space and time, is a robustly theoretical concept. It's something that's been really useful in successive physical theorizing, and we should look at theory to work out what kind of role it plays. And once you have some idea what the role is, then you can look in a new domain and see if there's anything that instantiates some or all of that role. And that's the kind of project that I think might be interesting in quantum gravity. So all of that is a kind of, if you like, it's a kind of research program for how one might go about thinking about how to say things about space-time in unfamiliar contexts. And so obviously lots of the interesting work is going to be done by actually thinking about the kind of role that space-time plays in our theories. But why might you want to adopt that general picture in the first place? Why do you have to be I think you kind of have to be a space-time functionalist, realistically. Why do you have to be a space-time functionalist? Well, it's because the alternatives are really, really awful. Even without saying anything about the details, if you're a space-time functionalist, you're committed to two views being bad views. And I think that when one thinks closely and hard about them, they're obviously bad views. But they are views that creep into our thinking in various ways when we theorize. So one is mathematical fetishism. That's not my term, it's John Stachel's. But this is my word for a view that says something like, look, there isn't much debate about how to find space-time structure in a theory. You write down a theory, it's got space-time structure, you write down a manifold, you whack a metric on it, you whack some affine structure on, and you've just described a space-time. So this question of how to identify space-time structure in a theory just doesn't arise. on any deep thought, that seems obviously a bad view, right? There are lots of cases in which we write down particular kinds of mathematical objects that don't end up representing space-time. And there are lots of different mathematical ways to represent space-time structure in different theories. So a purely mathematical criteria, without thinking about how the thing connects up to the rest of the theory, at which point we'll be thinking in functional terms, is a bad way to think about how to identify space-time structure. The other bad way I think we shouldn't identify space-time structure is kind of metaphysical fetishism. And by the way, you can be both a mathematical and metaphysical fetishist. I think there are some in our community. But the containment view person, right, thinks that it could be the case that you have some entity in your theory that does all the stuff that space-time does, but you could still imagine that the theory really lives in some different space-time. So whatever the content of really lives there is going to be, it's going to be not captured by what the putatively spatiotemporal object does in the theory. I don't really know how to make head nor tail of that view. I think some people think have an intuition about what space-time is. I suspect that that entire intuition is metaphor. Anyway, I'm happy to debate the merits of those views. I won't say any more about them now. But space-time functionalism per se is a commitment to not doing either of these things. It's a commitment to thinking hard about how the object you take to represent space-time links up to the rest of the theory in the sense in which it plays a kind of spatiotemporal role. Okay, but that only gets you so far. If you're just a woolly space-time functionalist, you can bash people, but you can't say anything very constructive. So I'm going to contravene this long and illustrious history in philosophy, right, of announcing that something's functional and then saying something like, it's C fibers firing, it makes you go, ouch. I think we'd like to do a little bit better than that in philosophy of physics. So if you want to actually apply to physical theories, you have to say something about what the functional role is. And I'm not even going to pretend I can say everything about what the functional role is, because typically in complex physical theories, some piece of structure plays a great many roles in the theory. But I think we can say some useful shorthand things about the functional role that space-time plays in existing successful theories, primarily relativistic theories, but also Newtonian theories. And the preview of that is that I'm going to say that the role for space-time is well picked out by saying that some structure is space-time just in case that structure defines a local structure of inertial frames. So I'll say more by what I mean by that. But how do you get there? Well, how does one go about thinking about the kind of role that space-time plays in our theories? Well, even if you're an out-and-out operationalist, which I think probably be clear by the end of this talk I'm not, but you would probably care about identifying space-time, and you care about it for just this reason that I mentioned earlier, right? You would care about identifying space-time because you want to get empirical predictions out of the theory. And you're going to hear overtones of the kind of thing that Harvey Brown says here, but when you want to work out the predictions of a theory, and they're often predictions in terms of distances and times, you don't go and model a rod or a clock or all of your measuring apparatus from scratch. You just assume that certain things are going to be well adapted to what you take the distances and times in the theory to be. And so that's a really important empirical role for space-time. When you say something space-time, at least at the phenomenological level, one of the things you're saying is it's the kind of thing that certain kinds of rigid bodies are going to survey in certain kinds of ways. So here's one desiderata, like a sanity check, for whether you've got a reasonable idea about what space-time is. In the phenomenological domain, by which I just mean, medium-sized dry goods and all of that jazz, the kind of domain in which we do physics, our functional role should be such that if a geometrical object instantiates it, then that object has its usual operational significance in terms of measuring rods, clocks, and light rays. And again, you'll hear echoes of Harvey Brown, who'll be on the next slide. If you want to ensure that, if you want to ensure that you're doing what Brown would call surveying the metric, right, you're going to have to say something about the functional role for space-time that links it to the rest of your dynamics. That's the basic sanity check. If you don't have any connection between space-time and the stuff that matter does in space-time, you're not going to have a space-time that plays anything like the role that we're familiar with. And here I think that you can pretty much just borrow from the Dynamical Relativists toolkit, their project. So Harvey Brown and Oliver Pooley originally proposed a shortcut to understanding why it was that rods and clocks and light rays told us about the geometrical structure, surveyed the metric, why the metric had chronogeometric significance. There is very sort of particularly brown kinds of ways of expressing this point. And their point was that if you understand the symmetry properties of the laws that govern rods and clocks, you can predict their spatiotemporal behavior. So if you want to make sure that all of your laws are well adapted to a Minkowski metric, so that all the stuff made out of those laws, made out of matter that obeys those laws, will survey a Minkowski metric, you just got to be sure that your fundamental laws are Lorentz covariant. Things get much more complicated in the case of general relativity, but ultimately, lots of caveats on this, and we can talk lots about the strong equivalence principle, but ultimately it's the strong equivalence principle in general relativity that ensures that the matter fields couple to the metric in such a way that stuff built out of those matter fields has some kind of operational significance with respect to the metric. Now, dynamical relativity is kind of a big project, and one presumably lots of people in this crowd are familiar with. So it's worth just saying, what I'm trying to do is kind of borrow one side of that project without necessarily all of its associations. So there are lots of different ways of reading dynamical relativity. On some readings, it has anti-substantivalist connotations. It has connotations about orders of explanation between space-time and other facts. Those aren't the connotations I wish to borrow. But there is this other way of reading the kind of project, and there's a nice paper by Wayne Mervold in an upcoming volume on Harvey's stuff. It's a festschrift for Harvard Brown that makes just this point. There's another way of reading this, which is that Harvey's work is in a sense one long conceptual analysis. Whether Harvey likes to see it that way is another question, right? But so one thought behind dynamical relativity is that in special and general relativity, the claim that the metric represents space-time structure just is the claim that the dynamics picks out a certain inertial structure. And that is the kind of language you'll see in that project. And so part of that, if you sort of think of that as a conceptual claim, when you claim that something represents space-time structure, you're just claiming it picks out the inertial structure. That's a side to this dynamical relativity project. Okay, so sort of borrowing the kind of work that's done there, that leads you to this view that I like, inertial frame functionalism. And you say, look, at least in our current theories so far, the kinds of things that we think space-time should do, the Desiderata that we might have had, are satisfied if we say that the space-time role is satisfied by some object just in case it specifies a structure of inertial frames suitably defined. Suitably defined is important there because some people just, in fact, Harvey himself sometimes says this, and then we sort of part ways. Some people say, oh, look, an inertial frame is just a frame in which a freely falling body travels with a straight line. But I want it to be a slightly thicker notion than that. When I say structure of inertial frames, I'm talking about a wider structure that captures something about the symmetries of the dynamics. So inertial frames are those in which non-gravitational interactions take a universal, simple form, and in which freely falling bodies move in straight lines. So you get this appropriate connection to the dynamics built right into the notion of inertial frame. It can't be an inertial frame and not be connected to the kinds of things that complex material bodies do. In the relativistic context, that gives you back everything you want from space-time. Inertial structure fixes projective and conformal structure, and hence full metrical structure, at least up to a scale factor, a global scale factor. Another way of thinking about that is that the Fermi normal coordinates, the inertial coordinates of general relativity or special relativity for that matter, are coordinates in which the metric takes a particular form. And if you know how to write down the metric in one set of coordinates everywhere, you know how to write down the metric. That's just what it is to write down the metric. So why might you not want to be an inertial frame functionalist? You're all persuaded. There we go, stop there. Well, certainly lots of people find there to be some things to object to in this. One thing that is sort of part of a wider debate, but proves a bit of a sticking point, is that I'm going to talk about coordinates. And one of the nice things about the example I'll use at the end of this is I think it's going to slightly justify why you might sometimes want to talk about coordinates. But one of the lessons that a lot of philosophers of physics take themselves to have learned from, say, general relativity, and certainly some physicists do too, is that we learned that, we shouldn't be thinking in coordinate-based terms. It's always better, more foundationally pure, more interpretationally clear to think about things in a coordinate-free kind of way. This kind of view ends up a bit tied to the kind of the people you might think of as mathematical fetishists, right? You just write down these beautiful geometrical structures, and that's what we should be doing. I genuinely think people throw the baby out with the bathwater on that approach. Of course that we learn something about the value of differential geometry when we do GR, and our ability to transform between coordinate systems and to express certain things in abstract terms is very helpful. But I genuinely meet, usually sort of grad students, not, often not everyone, although some very smart people, I've genuinely had arguments about whether you can get empirical predictions out of general relativity generically without using coordinates. And some people really maintain that we don't need coordinates for anything, and which shows you that philosophers don't do enough physics, right? You have to use coordinates eventually. So in as much as we're concerned with the empirical and operational significance of the theory, coordinates are really important. You could also push back generally on the idea that coordinate physics isn't fundamental. So there's a really nice paper by David Wallace called Who's Afraid of Coordinate Systems? Right? And part of his point is just that there's a very natural way to think about geometry that starts from a kind of Kleinian conception of geometry that starts from coordinates. And I think that there's a lot in that. It's not, and it also needn't compete with a kind of geometry-first approach. I think we may have over-egged the value of coordinate-free approaches. The other thing that we'll see later is that there may be cases in which it's just not right to take a coordinate-free approach. There may be scenarios we can end up in, and quantum gravity might put us in, that threaten the kind of moral that people take to have taken from general relativity. So that's my rant about coordinates. If you don't like other aspects of inertial frame functionalism, one thing I should be pretty clear on is that this is a kind of shortcut. You could list, if you were kind of doing a kind of full list of everything spacetime's ever done in a theory, you'd write down a long, long list of things. And it wouldn't do the same thing in every single theory. Its role in Newtonian mechanics would be different from its role in special and general relativity. The inertial frame role is a kind of shortcut to a whole load of the things we're interested in, and one I think that's going to be an interesting way of finding a big chunk of the spatiotemporal role in future theories. But I don't suggest it as a once-and-for-all analysis. If we come up with theories that don't have anything like it, full inertial structure, that doesn't rule out ever talking about spatiotemporal structure. Again, this is this kind of conceptual tracking exercise. But I think this is a particularly interesting role because of these empirical associations in particular. Okay, so let's just remind ourselves about what inertial frames look like in general relativity. In general relativity, they're associated with the Fermi normal coordinates along a time like geodesic. So at the origin of those coordinates, the connection coefficients vanish and the metric looks Minkowskian, and then just off the coordinates, the metric will take a particular form, depending on the curvature and the distance away from the coordinates. But what you approximately get is something that instantiates the closest GR has to an inertial reference frame. Right? And the strong equivalence principle is the bit of the theory that tells you that the matter fields are going to be written down such that when the metric diagonalizes and the connection coefficients vanish, then you're going to get back a particularly simple form of your theories. Okay, so that's the inertial frame functionalism section done. And now on to attempting to apply it. I'm tempted to move in front of the air conditioner around about now. Right, am I allowed to do this? Oh, so much better. I'm going to have to listen to it. In the following section, we'll try to apply some of these morals to a particular case. It's all right, I'll just be hot. I know, but then the hands get... It's fine. All right. So what I want to do now is just tell you a little bit about non-commutative geometry. Now, there are people in the room who know lots more about this than me. In the question session, you can address all technical questions to Nick Huggett. Probably there are others in the room that know lots more about this than me as well. I'm going to try and sort of give a sketch of what I take the kind of conceptual framework to be here and what's going on. Hopefully it's sort of a conceptually helpful sketch. I'm assuming that anything more detailed than this isn't the kind of thing that anyone who doesn't know about this stuff is going to absorb in a single talk. So maybe here's a helpful thing to say, because some of you may know a little bit about non-commutative geometry. As far as I can tell, and I'm having trouble tracking the history of non-commutative geometry, because it's not exactly the kind of thing anyone's written a history book about, but there are kind of two roads to non-commutative geometry. Right? You can start by thinking about quantum mechanics and C-star algebras and Hilbert spaces, and you can think about non-commutative geometry that way and then think, how might I apply that to space-time theories? Or you can start another way. You can start with general relativity. You can start with ordinary classical spacetimes and think about how might I give an algebra, an algebraic formulation of those kinds of theories. And then you might think, what happens if I make things go a little bit quantum and go non-commutative? And hopefully the two approaches sort of end up in the same place. The first one, I think, is the kind of Connis style non-commutative geometry, and as I think it sort of ends up in the same place I'm going to go to today, but the sketch I'm going to give follows this slightly alternative route. So if you've sort of done a bit of the kind of quantum-y, C-star algebra kind of non-commutative geometry, this might look like a different route. It's a route that would be more familiar to somebody who studied general relativity. Okay, so on this route, start with just ordinary familiar differential geometry and recall somewhere from, some reference to Einstein algebra somewhere that it can be given an algebraic formulation. So this is the kind of thing that Bob Gerock did in 1972 and John Ehrman used when he was talking about the whole argument, if this sort of triggers bells in the minds of philosophers. So what you now think of is you start with your manifold structure, but now you try and think of that structure as being well exemplified by an algebra of fields. So you start with C affinity, set of scalar fields, and their algebra itself is going to provide the topological and differential structure of the manifold. So you're going to recreate the manifold by thinking of the sort of set of smooth fields on the manifold and its algebra. And then you give other aspects of differential geometry an algebraic characterization. So there's some, you can think of some of these things as being very natural. Vector fields are represented by the class of derivations, which are the automorphisms of the C infinity that satisfy the Leibniz rule. A metric is an isomorphism between D and D star, that's symmetric. I mean, you can go on and look up the definitions of these things, but it's fairly natural to think of, you can represent geometrical things by sort of purely algebraic structures. I mean, we do, in fact, define derivatives, via something like an algebraic rule. You're just doing something like that here. And it turns out that you have what mathematicians would talk about as an algebra-geometry duality. There's an entirely one-one relationship between this algebra of fields and structures definable on it, and what we think of as the normal differential geometric structures on the manifold. And you can show that these two things are logically equivalent. So you can write down an algebraic version of general relativity, for example. Or at least you can write down all of the geometry of general relativity in an algebraic version. Okay, so now, I don't know whether the thought is, I'm sure the thought is much deeper and more sophisticated than that, but you could have the following thought. Well, I want a theory of quantum gravity, right? And, non-commutativity is like what's really essential about quantum mechanics. So let's get non-commutativity into a geometrical context. And once you've moved from thinking about, we'll say a little bit more about what it might mean to be non-commutative on the manifold in a second, but if you think about ordinary geometry, just, you can't get yourself out of commutativity. But once we've moved to this algebraic formulation, it's pretty easy to introduce non-commutativity, right? I just take the product and I make it non-commutative. And I add a theta factor, a deformation factor of some kind. So I define a new algebra. Algebra of what, you might ask? Well, that's a very good question. Ask Nick. Algebra of elements that are meant to be analogous to the elements in the old commutative theory, but now we're not thinking them as obviously fields on the manifold. So I define a new algebra, and coordinates and polynomial functions of coordinates no longer commute in this algebra. So I end up with a theta factor, non-commutativity factor. But I can still define all of the differential geometric stuff that I did in the previous case in the same kind of way, because most of the rules they're definable in the presence of non-commutativity. So I just define things like, the equivalent of tensor fields and derivative operators, etc., in the same kind of way. And then the particular kind of non-commuting geometry I'm going to be talking about is going to just be defined by putting conditions on that. Putting conditions on that. There we go. On this theta factor, right? In particular, you're going to end up with generally you're going to end up with a kind of a non-commutation matrix, if you like, that in what's called canonical non-commutative geometry is taken to be a constant real valued antisymmetric matrix. But what kind of non-commutative geometry you're talking about is going to be kind of defined by putting conditions on this theta. That's important because it's going to turn out that the conditions on this theta aren't easily expressible in anything like sort of ordinary coordinate geometry on the normal manifold. Okay, so this algebra, unlike our commuting one, isn't dual with something in differential geometry, right? There isn't a representation theorem It doesn't have a direct analog in familiar manifold geometry. But you can, if you want to try and extract empirical content from a formal system that uses the non-commutative algebra, map the non-commuting algebra back onto the commuting algebra, right? And thus sort of place it back on the manifold, right? So you're trying to think of how to represent this non-commuting theory on a manifold. And the manifold's fundamentally not well adapted to non-commuting geometry, but we can do it nonetheless. So there's this thing called the Weil transformation, which is the transformation you induce if you map non-commuting coordinates back to the commuting coordinates of your commuting algebra. And what that gives you is a representation of the geometry of RD theta, your non-commuting algebra on the manifold. But what you're doing effectively is you're trying to write down a theory that isn't well adapted on the manifold. So you pick up kind of odd things along the way. And most of those odd things are summed up by the fact that the product, you stop using the product that's naturally adapted to the manifold structure, and you start using the Moyal star product, which has a whole ton of theta factors in it. So, people do sort of do dynamics of sorts in this theory, but just at a very programmatic level, but I don't know how to do all the dynamics of theories like this. At a very pragmatic level, anytime you kind of need a product, right? These are functions of your coordinates. This looks like the kind of stuff you need to do physics. If you want to do physics in this theory, you're going to be constantly, and you're writing it down as represented on the manifold, you're going to be constantly picking up these theta factors when you do your physics. So the dynamics of the theory is going to involve the Moyal star product and not the ordinary product. And that means the dynamics is, in a certain sense, badly adapted to the geometry into which you've mapped it. So you have this commuting geometry and you kind of mapped this non-commuting theory into it, but you end up with a dynamics that doesn't kind of respect the commuting geometry to which it's mapped. What does that amount to? What does that mean? Well, and this, especially for someone who kind of does foundations of space-time theories, this is really weird. What this means is that these theories don't reflect the diffeomorphism invariance of the commuting geometry. And I think so this is something that everybody who works in this stuff, sort of, you find this in the papers. So, these theories aren't diffeomorphism invariant. And that, you might think that sort of sounds surprising, right? So I think what that means is that this thing, we defined, so canonical non-commutative geometry is defined by the constancy of the theta matrix, right? So we put a condition on this thing, we say it's going to be a certain kind of matrix in the fundamental geometry, in the non-commuting geometry. But that thing isn't invariant under ordinary coordinate transformations. And it's not just that it doesn't transform like a tensor. I think, as far as I can tell, it just doesn't have transformation properties. It's only, we'll say in a minute, it's only going to be well-defined in certain coordinate systems, which is very odd, conceptually, right? If you're thinking of the real space-time as being the one described by the commuting geometry. But the trouble is the dynamics all depends explicitly on this thing that you can't write down in arbitrary coordinate systems. And it turns out that this thing is only constant, and indeed I think can only be written down with respect to a privileged class of frames. So put it this way, I certainly can't work out how to transform theta arbitrarily. Now I think you can make some kind of conceptual sense of this when you think about things the following way. What's the analogue of a diffeomorphism in a non-commuting geometry? Well, you can think about the homomorphisms of the RD theta class, and that's the analogue of the diffeomorphisms of C infinity. But if you go back into your non-commuting geometry, perform a homomorphism, then map yourself back into the commuting geometry, that transformation there, that generates a subclass of the diffeomorphisms, not the full diffeomorphism group. I don't know if that helps or makes sense. So part of the thought is that there's actually a particular class of coordinate transformations in the ordinary commuting geometry that are kind of natural transformations with respect to the non-commuting geometry. Now, this raises interesting and puzzling questions, right, about the very possibility of a generally covariant form of a theory. I've certainly had lots of sort of pushback from philosophers that you have to be able to write down theories in generally covariant form, right? Kretschmann told us that. Of course, I don't think, there's some sort of, you can have some kind of programmatic ways of understanding what Kretschmann was saying, but they're all going to ultimately rely on commutativity at some point. But generally, philosophers have taken it sort of as writ that it's true that any space-time theory can be written in generally covariant form. And this is, I mean, simple is the wrong word, but a relatively simple example, at least, sort of a way that you could get to writing down a theory that simply can't be written in arbitrary coordinates. It looks like theta mu just doesn't have well-defined transformation properties. And you always define, if you try and construct the differential geometrical objects that are meant to give you the generally covariant form of your theory on a kind of Kretschmann prescription, you have to know how stuff transforms. You just rely on the fact that you know how to write stuff down in more than one coordinate system. So I think the usual techniques just aren't going to work here, and we just have to accept that this is something like a theory that can't be written in arbitrary coordinate systems. Okay, so what should we say about the theory? Well, this is the bit where it gets the kind of the grist to my mill stage. There was a student who recently commented to me that nobody outside a philosophical classroom ever uses the phrase grist to my mill, which is very true. But anyway, this is grist to my mill. What other phrase could there be for it? There's a nice little paper, which kind of, I mean, it's puzzling in various kinds of ways because I find some of the methodology in this field puzzling, but in which this group of people derived some results from a model of non-commutative gravity as a gauge theory. So there is something, I mean, there's lots of subtlety I'm glossing over here. These guys are using, there's kind of gauge theoretic way of constructing these things where you use the Seiberg-Witten map instead of the Weil transformation, etc. But I don't think that makes any significant difference to the moral here. So one of the things that they do, and this sort of result is standard in as much as anything in non-commutative geometry standard, is that they show that the non-commutativity leads to curvature and torsion in the adduced geometry. So the idea is that theta factor, and this is where you see how this might be a theory of gravity, right? That theta factor is a source for torsion and curvature. At the moment, it's constant, right? And so it's, they talk about it being something like the cosmological constant when they talk about the curvature. So we're a long way away from getting out general relativity. But anyway, there's this tempting idea that the theta factor is a source term for the kinds of things that we associate with gravity. And how the methodology of this kind of paper works is you start with the Minkowski geometry and you take a perturbative approach to finding the Weil transform of the non-commutative covariant derivative and the metric with the torsion and curvature depending on theta. So you basically work in the weak field limit and get out some extra terms that depend on theta that are meant to tell you about the geometry. So as I say, that's all relatively standard, but what's non-standard and nice from my point of view, kind of interesting, is that they show that the coordinates that theta is constant with respect to, so the coordinates theta is kind of well defined with respect to, are the Fermi normal coordinates of the induced metric. So they get out this kind of induced metric via their theory, and then they show that, and they do all that in coordinate terms, right? So they do all their calculations in coordinates, and then they show that the sets of coordinates that their equations hold in are the Fermi normal coordinates of that metric. So obviously I like that because, of course, this looks like a kind of pathological theory, but in which we can find something that resembles the role of space-time structure. You've got this crazy geometry. You're a million miles away from what the mathematical fetishist wants. But nonetheless, there's this sense in which this theory is adapted to this particular kind of space-time structure. But if you're just faced with a theory like this, what do you say about its geometry? Right? What do you say about its space-time? There's actually a whole load of different geometries going on in a theory like this. And this is sort of one of the things that's led me to the kind of thought that I have is all the many ways in which geometries can kind of fail to coincide. It's one reason why mathematical fetishism isn't a good option. So you've got the fundamental non-commutative algebra, you've got this wacky geometry that we're not very familiar with. You've got the induced affine geometry on the commutative space, given by a covariant derivative with torsion, because remember theta is a source term for torsion. You've got an induced metric geometry on the commutative space. And you've got a geometry picked out by the preferred reference frames of the fundamental dynamics, once they're kind of represented on the manifold. And these two things coincide in this case, but generically, if you have a connection with torsion, it doesn't generally, a metric compatible connection with torsion, its affine geometry doesn't agree with the metric geometry. So you've got multiple candidates for geometries here, if you like, for what the real space-time structure is. And so that should raise lots and lots of questions, right? If you're interested in theories of quantum gravity, you'd want to ask questions about the correct interpretation of a theory like that. So, does this involve space-time at all? If so, what should we say about it? How does phenomenological space-time fit in here? Is this an emergent space-time theory? Now, I'm not going to pretend that I'm far enough along in this project to sort of have really well worked out argued answers to all of these. But what I do at least want to convince you of is that adopting something like a functionalist approach, and preferably my functionalist approach, obviously, is the best way, and really the only possible way you could start to answer questions like this in this kind of context. Let's start with the first question. Does this involve space-time at all? Well, then you've got to have some notion of how you know space-time when you see it. And a functionalist is going to have a notion, and on my functionalist interpretation, you're going to say, look, yes, it looks like there really is a space-time here. It looks like there's a privileged structure of inertial frames here in a particular sense, at least in a sense that there's a class of frames in which the dynamics, the fundamental dynamics, the non-commutative dynamics, takes a simple universal form. What happens to force-free bodies here? I haven't the first clue what a force-free body looks like in non-commutative geometry when it's at home, but at least I could, look, so again, concept tracking. We might have lost that bit of the inertial frame concept, but we've still got something that looks pretty familiar. And then we can ask ourselves whether, if we're building bodies out of these dynamics, whether they're going to have the right kinds of associations. It looks like it's a fairly good bet that they might. Of course, this is where quantum gravity is hard, right? Because we don't know how to build bodies. Okay, so if that's the case, what should we say about it? Well, now you can begin to make sense of some of the kinds of interpretive things that people say in this kind of field. They say things like space-time itself isn't smooth. And I take it what they mean by that is that the manifold structure itself isn't particularly playing a representative role of space-time here. There is something like this kind of effective structure of inertial frames that looks like the kind of effective structure of inertial frames we get from a metric on a manifold, but you're not thinking of that as the fundamental thing. So it's the non-commutative geometry itself that's picking out that class of inertial frames and playing the role of space-time structure here. What happens to our kind of phenomenological space-time, the space-time that we do physics in? Well, I mean, again, hostage to the details of how you work out a theory like this. But presumably, it's the one described by the metric on the manifold. If you pretend that this project is complete and that somehow someone works out how to get GR out of this theory, and these whatever much more complex dynamics conditions you better put on the theta factor to come close to doing that, gives you back general relativity on appropriate length scales, then presumably what you'd have in this highly counterfactual situation is a scenario where you have a fundamental explanation for the privileging of certain frames, because you're told in terms of the fundamental dynamics why these frames are particularly important. And so it looks like you'd be told why phenomenological spacetime is the way it is by the theory at hand. There'd be more work to do there, filling out all the details. Is this an emergent spacetime theory? I mean, I do have views on what constitutes emergence. I could weigh in with them. That's kind of a different segment of work. I mean, I think perhaps not. In our fictional case, where GR comes out of this theory, the metric structure of general relativity appears to arise pretty directly from the non-commutative theory. So if you think emergence implies certain kinds of abstraction, idealization, limiting procedure, if you find the structure just kind of sitting in your non-commutative geometry, you might think that it's not really a case of an emergent space-time. It's just a case of a really weird space-time, not necessarily an emergent space-time. Okay, so that's it. Let's say those are sketched answers, not filled out answers, but what I really hope to persuade you is that at least adopting something like inertial frame functionalism is going to provide interesting answers to the kinds of questions that you get raised in this very strange context. And I think that model is going to go over into other cases where we're in very, very odd counterintuitive contexts as well. It's hard to see how any non-functionalist theory could tackle those questions. And also, I mean, this sort of cropped up out of thinking this rather than being my aim. But I also think that there's another sort of lesson for us in the foundations of space-time theories, which is that the existence of that kind of theory might cast some ideas on things that are standardly said about general covariance. Right, thank you very much.
We will meet the microphone for questions.
Okay, I'll run around.
So can I ask people please to hold the microphone reasonably close to the mouth so that it actually can do its work? Thank you. So Pseudo is the first question.
So I have a couple of questions. One is, so at the last, like towards the end of your talk, you focused on a particular kind of non-commutative theory, which is basically framed on flat spacetimes, and then somehow whether we can know anything about general spacetimes. But in the beginning, you were talking about non-commutative gravity theories in general, where you formulate the theory in completely general spacetimes. In that case, I don't see. First of all, why there should be a problem if it is not diffeomorphism invariant, because just like you are deforming the manifold now to be non-commutative, you can also deform the diffeomorphisms, and so there will be deformed diffeomorphisms. And also in that case, space-time can easily be emergent in this limit that the theta goes to 0. Indeed, quantum mechanics can be formulated as deformation quantization, where h bar, when you take that to go to 0, you read classical mechanics. So the same procedure should be present here, right?
Okay, so I think I'm going to try and translate the language. So I don't think it makes sense to say the manifold can be deformed to be non-commutative, or the diffeomorphisms can be deformed to be non-commutative. I think what you mean is chuck out the manifold. We just know we don't have a manifold structure anymore. We have a non-commutative algebra. Because it's
non-commutative manifold. A manifold with non-commutative properties.
Okay, so I'm puzzled by that locution, and maybe we need to talk more about it. I mean, the standard definition of a manifold isn't reproducible in the non-commutative context.
No, the standard one.
Okay, so I don't know how to do the non-standard one. So anyway, so I guess, the one I know from geometry textbooks you don't just quickly turn off the commutativity. And I take it what you mean by deforming diffeomorphisms is just this thing that I mentioned, which is that the homomorphisms of the non-commutative algebra, let's say, they generate a sort of subclass of the diffeomorphisms. So I mean, that's one way of thinking about the deformation. But maybe this is what you're trying to say, and I take it I'm completely sympathetic to. If we just don't worry about the representation of this stuff on the commutative manifold, if you want me to call it that, it internally makes perfectly good mathematical sense. There's a set of homomorphisms, and there's an algebra. The problem comes when we try and actually work out how to do physics and how to link it back up to empirical stuff. So, as far as I can tell, there are various different ways in the literature to do that. And yes, it's absolutely true that the kind of presentation I was giving is just one. But all of them are going to have this very strange phenomenon. If you move back to trying to represent these things effectively with commutative coordinates, which is what you're doing when you move back onto the manifold, there's going to be a kind of a mismatch between the structure you take to be fundamental and the one that you're using to try and represent that structure to get the empirical content out of the theory. And it's that writing down of the theory in a way that sort of, is empirically accessible, that looks like it can't be made diffeomorphism invariant.
So just one point is, this is all true if you assume that diffeomorphisms or the homomorphisms now are a subgroup of the diffeomorphisms. But indeed, if these diffeomorphisms are deformed such that they are seen as a group, they are infinite-dimensional, and they have the same number of generators as diffeomorphisms, then none of this needs to be true. So I agree with the statement at the end that general covariance might be too restrictive an idea. What needs to be replaced, what needs to replace it is some sort of deformed version of general covariance. But in that case, everything else can be formulated in the sense of symmetries and so on. I think that's right. We can talk.
Okay.
Very interesting. I don't claim to understand this non-commutative stuff, but you said enough things that give me a feeling of what may be going on. When we talk about the construction of Riemann or Fermi normal coordinates, we make use of geodesics.
Yep.
Geodesics that are presumably followed by 3 point-like particles that I throw. So I start from one point, I throw around these particles and use them to construct the coordinate frame. And then your claim is that this parameter will appear as torsion, which of course will not affect the geodesics of free particles, but it will affect the motion of particles with spin. So in this frame, in which I obtain...
That depends how you write your dynamics down, right? That's an important lesson. I mean, it's not like torsion magically couples to spin.
Assuming
yeah.
Assuming that's what happens, then in some sense you already have a recipe to test this idea, right? Let me construct my frame with these free particles, point-like particles that have no spin, use them to construct currents, and now let's see how a spinning particle behaves. If it follows a trajectory very different from the ones that would be followed by, then I would be measuring this theta parameter, and in some sense that's the prediction of the theory. It would be a space-time that is different from the one we explore or we're used to exploring, but it's seems to be a perfectly conceivable space-time on which we actually could put constraints on this theta parameter.
So maybe it's just best to say some general things about theories with torsion there, because there's something I've thought about in a sort of independent context. So yes, that certainly could be the case. I think one of the things, the morals that I'm hoping to draw out, and I think that very explicitly what kind of got me started on this was bits of the physics literature where people wrote down connections with torsions and then thought that the stuff you were just talking about would magically happen because you'd written down a connection with torsion, right? So because you've written down a connection with torsion, suddenly you've affected the motions of spinning particles. Of course you haven't. There are reasons why people have associated torsion as coupling to spin degrees of freedom in particular kinds of ways in the past. And maybe there are some conceptual reasons for that. But it's not in and of the nature of having written down any old object in your theory with torsion that you've got any connection to empirical stuff whatsoever. Everything depends on how that covariant derivative operator behaves in the dynamics. And it's very easy for those two things to come apart. And in particular, theories of torsion are rather odd because in general, the symmetric part of the torsion-containing metric-compatible connection isn't the Levi-Civita connection. So you've kind of just got these two senses of geodesic, because you've got the geodesic defined by the symmetric part of the torsion-containing the connection with torsion, and you've got the Levi-Civita connection. So I wouldn't have thought that you could generically now, if you discovered that spinning bodies did something very different from non-spinning bodies, and you'd have to be careful about what kind of, because I think extended spinning bodies don't follow geodesics anyway, even in general relativity in the absence of torsion. But if you discovered that spinning bodies did something very different from non-spinning bodies, that might be a hint that the right theory really would have torsion. But I'm not sure it goes both ways. I mean, you might have your torsion couple in various other kinds of ways and do all kinds of crazy things in your theories, and you need to puzzle out how that works. I guess that's.
I just want to ask a bit more about the functional account of inertial frames, especially in the light of the comment that it might be multiply instantiated within any given theory. That I guess threw me a little bit. I guess the way I'm used to thinking of them is kind of their descriptions in which the laws of physics take the simplest form, but how will that allow for multiple inertial frames in the given theory? Is it like ties for the simplest? Presumably they're not going to be, what kind of forms the laws take aren't going to be simple in exactly the same respect with the different kind of inertial frame candidates within any given theories. Is it like there's a kind of function of simplicity across theoretical components and you can have a relevant minima if like you get inertial frames, or is it like anything where they're simple enough is what gets you an inertial frame?
So I actually hadn't thought about the case where there were two simple forms for the theory. I mean, I'd have to two simple forms for the theory of different classes of frames, two different simple forms. I was actually more thinking about cases where you could talk about domain-specific inertial structure. So it seems like you can have effective inertial structure really easily, right? As long as certain assumptions are met, the laws take a particular form in particular reference frames. But, if you look on small scales, they don't, or if they, So it seems as if it's the kind of notion that could, for example, be scale relative, could be domain relative really easily. And in that case, you might say, well, when I'm in this domain, I'm talking about this set of laws, and they're picking out this particular structure. And to some extent, we do this whenever we think about, whenever people think about, having something like Lorentz covariance be approximate, come out of theories approximately, right? So if you've got something on very small scales that violates Lorentz covariance, you still have the special relativistic inertial frames operative at the level that that you can't feel that structure at. So that's the sense in which I thought you might be able to have more than one of these structures. And that's the sense in which I think this kind of approach is well adapted to these kinds of weird quantum gravity cases where we really might want to be saying different things about space-time structure at different scales and different domains.
Here's one thing that has always puzzled me in the philosophy of probability. Somehow people seem to think that there needs to be one way to interpret probabilities. Maybe it's subjectivist, maybe it's frequentist, whatever. One way, the one right way to think about probabilities. And that one right way to think about probabilities then is somehow supposed to apply to all theories in which we apply to theories. It's always been completely mysterious to me why that's somehow a priori true. Because it could well be, of course, that probabilities in GRW may be the best interpretation for those probabilities is very different from probabilities in Bayesian epistemology and what have you. You know, probabilities, maybe there are different right ways to think about probabilities in different theories. Now, this is why I bring this up, in case you're wondering. Maybe there's different ways to think about space-time in different sort of theoretical frameworks. And I'm very curious to see what you think about that. For instance, one could say, look, if you're working in quantum gravity, where you realize space-time as such is really not comfortably there anymore in any of those theories, this gives us excellent motivation to become space-time functionalist. If things become really weird, non-space-time-like as they used to be in GR, by being non-commutative or wild in a number of other ways, there we have excellent reason to become functionalists. However, these reasons do not apply to GR. In GR, we should be good old-fashioned substantivalists. There's this one substance described, you know, by the geometrical structures so beloved by the church of the angle brackets, you know, that sort of approach. There, it's perfectly natural to think in substantival terms, and there's really no additional reason for us, or the reasons, whatever they may be there, are much milder to go to a functionalist picture than they are in quantum gravity. What do you think of that sort of objection?
Okay, so I was with you and not thinking of it as an objection until right at the end, right? So one of the things that I think about functionalism is it's naturally ecumenical. So there can be all kinds, like in our current theories, things play different roles, and those roles overlap, and those roles can come apart in future theories. And actually, I would think exactly the same thing about probability. So probability does a load of stuff for us. I'd actually think you want to give probability a functional characterization, but you might want to have, you might think that there are multiple different functional roles that probability could play, and those could come apart in strange scenarios, and that quantum mechanics might test us in various ways. So that's how I think about space-time structure. I'm not, as that this is the sort of sense in which I'm not totally wedded to inertial frame functionalism. There was this debate between me and Simon Saunders about how to think about Newtonian gravitation in light of accelerative symmetries, and one of the things, David Wallace wrote a nice paper about the two conceptions of space-time we were using. And I think that was exactly right. There's a sort of conception of space-time where it provides a background geometry in a very particular sense, in the sense of defining this sort of maximal symmetry group of the fundamental dynamics. And that's slightly different from my conception. But that first one's still functionalistically, you know, you can still define it as this structure does something in your theory. So as long as you're really clear which notion of space-time you're using, I think the functionalist can be happy. I suppose I simply think that the other the non-functional alternatives are so ill-defined that I don't even know what it means to say, in GR, I'm not a functionalist. I mean, I think you can be a substantivalist in GR if you think that the thing that fills the functional role of space-time, the metric field, is part of your fundamental ontology, and you think it deserves the term substance, or however you define substantivalism, then you're a substantivalist in GR. I think that's what I think about GR. You should be a substantivalist. But if you want to know why I'm a substantivalist because it's something that fills the functional role of space-time that I appear to be fundamentally ontologically committed to.
Okay, that's very helpful, but you might say that the reason why I'm a substantivalist are not the functionalist reasons.
Yeah.
There I have different reasons to be substantivalist, independently of functionalist conceptions, which, however, become super useful once I go beyond GR.
I mean, so one thing to say about that is that those, I mean, I've yet to see a version of those reasons I don't think are bad reasons. So some of it's just a negative project. The other thing is, I mean, I do think when you look closely at the structure of GR, I think this is a kind of moral you can draw out of Harvey Brown's work. I mean, you know, GR isn't sort of magically well adapted. It's this very carefully crafted theory where everything's fit together in just such a way that the associations largely come out right. But not always, you know, sometimes it's approximate, sometimes it's... So even in the GR context, it looks like maybe functionalism is helpful in some kinds of puzzles, I think. So, but largely the reason I think that we should be functionalists everywhere is because, you know, really, I mean, you'd have to give me a good version of a non-metaphorical, containery, substantivalist argument why, you know, and I guess you'd have to be more sympathetic than me to kind of table banging, this is my... And then, well, maybe I'll say this: table banging, kind of, this is my metaphysical conception of the universe, and thus it must be right. I mean, if you're willing to countenance the possibility of these theories of quantum gravity, then that metaphysical intuition has got to be way off. So then, what kind of role is it playing in our interpretation of GR? Maybe that's something. Hi.
Thank you. So I'm going to have an example. The example might be too exotic, and I just want to push away from it, and I'll hand the microphone to someone else. Consider a world in which none of the inhabitants have any experiences which can be described as being of extended objects. So it's with respect to everything they know about the physical world, there is no extension. Now it so happens that they model their physical observations and their experiences with a complete algebraic theory. Let's say this algebraic theory can be mapped into another mathematical structure which has a manifold with local inertial frames. Would we say, so they could use this other geometric expression for their experiences, though they don't really understand what extension means in this mathematical sense, they just have a mathematical structure. But since it's playing the same functional role, would we say that world has space-time?
Well, here's a way to turn it around. I mean, could there be non-spatiotemporal beings in a universe like ours? Or maybe, you know, maybe their experience is structured along some other parameter. Ours tends to be structured on space and time. I assume there has to be something that kind of orders and structures their experiences, but I don't think it's completely impossible to imagine a single world existing with both kinds of things. I mean, look, put it this way, I mean, in their world, now if we are living in that world, we're still going to be interested in the space-time concept, it's still going to apply, and it's still going to refer to a real structure in the world. If you're those other beings, and obviously they can't come to communicate with us, we're doing mad sci-fi right now, but you know, they're not going to come to know about our concept of space-time realistically, but should they happen upon this structure, they can happen upon the structure and discuss the functional role, and part of the functionalist approach is that there's nothing more to talking about space-time than doing that. It's not, you know, then it happens that this particular functional role is interesting to us in various ways. But I don't see why you can't think about a universe that has something that's structured in the same way, that plays the same kind of role, where there are no conscious beings to be interested in it. It doesn't seem... and part of the functionalism ideas is not a fundamental metaphysical category. It's just a structure that's playing a certain role. So yeah, I mean, that universe has space-time, but there's no one interested in space-time in that universe.
Yeah, it's a rather deflated notion of space-time.
Oh yeah, I'd like to be a little deflationary.
No, that's fine. So you say there's space-time in a world in which there's no beings which have an experience of extension.
Yeah, I mean, if you don't want, I mean, cluster concept, you can chuck into your space-time concept that it's got to hook up to experience in a certain way, and then you're going to have thrown out that. But there's going to be something recognizably in this theory that we can talk about playing the same role, so I think, yeah, I mean, you can have all kinds of arguments about which concepts apply in a universe without beings that have concepts like ours, but...
Richard.
Two related questions. The first one is more general, and the second is more specific. The general question, which maybe I should forget to both questions for this one. The first question is how this relates to what people call the Canberra plan. That as metaphysicians investigating something like pain or causation, we look for that in the physical world, which is the closest realizer of our common platitudes. And you made a few remarks which suggested that's definitely not what you're up to. And good to me, in this case and more generally. But the more specific question is this. Physicists seem to talk a lot about something they call Euclidean space-time. And I could never get my mind around there being such a thing. It's fine to have a non-commutative metric for certain purposes, a Euclidean metric, but to suppose that that could play anything like the space-time role never made any sense to me. Now, on your view, one can give an argument as to why it shouldn't make any sense, because to connect up with the behavior of rows and plots and operational constraints, we need to look into some dynamics, and dynamics is making a distinction between a temporal dimension and other dimensions. So if there's no such distinction, there's no dynamics, there's no rows and plots. Would you go that way, or is it being too radical?
Okay, good. So first question first. Canberra plan metaphysics. Yes, I want to dissociate from big chunks of that. So one is the fact that folk theoretic platitudes have any role in this particular project. This is a robustly theoretical project, and I really don't care what people's folk theoretic platitudes about space-time are. I care what it does in the physics. And the other thing I think that can look bad in Canberra plan style metaphysics is sometimes it looks like when you've collected your folk theoretic platitudes, you provide the kind of once and for all an analysis, and that shouldn't shift. And I think that those two things, I'm sure there are people who think of themselves as Canberra plan metaphysicians who are more subtle about the concepts than that. But I want to disassociate from those two things. There is an echo of that project, because I think the project of thinking hard about the kind of role that something plays in our reasoning and in our conceptual structure, and then looking in a theory or in the world to see what fills that role, I think is a big part of what one can usefully do when one's trying to. So that picture of what we might do with conceptual analysis, looking for a role for something and looking for a realizer of that role, I think that, roughly speaking, seems right to me here. So first part of the question, there are overt, I think my PhD thesis had like a little mad space-time and Martian space-time example. I went that Canberra. I've become less enamored of using that language when I see how philosophers of physics react to it. So I choose my context carefully. I think yes, but with respect to your second point, I think probably yes, absolutely. I think that Euclidean space-time, it's not a space-time. It might be a space, right? And we could talk about another functional definition of a space, and it's just partly this just sort of casual talk. But I think we've got to be really careful with the casual talk, precisely because I can't see getting the kinds of operational associations we have with space-time. Light rays aren't going to survey a Euclidean space-time. You can't write down dynamics for that. So you could have a functional notion of a space that had something to do with symmetries in another sense, and the groups of available rigid transformations or something, and you could have a four-dimensional space that played that functional role. But I think that space-time, it's important that space-time does something in our theories that's different from what space does. And so yes, I'd be happy to say that at the very best, talk about Euclidean space-time is loose talk, and we should be very careful with it.
You managed to introduce your space-time functionalism so persuasively, I think that I really could not. It was not actually an unambitious position, because you introduced local and characterization of parameterization is already a technical concept. So I wonder what actually is excluded by it. Maybe you could clarify this for some of us by saying what would be the opposing position that you would be most afraid of, that you would take most seriously, right? So that we could see
Sure. Well, I only did it very briefly, partly because there are so many people in this audience that have been bored with me bashing the views I don't like before. But so let's take mathematical. So what I call mathematical fetishism, for example. Here's a view. So here's a. Let's take an example of that. In fact, this links up with the kind of thing I was saying about torsion, right? So there are a group of people. This is sort of early work I did as a grad student. The badness of it made me think. Sort of what inspired some of these views. So there are a group of people who think that you can have not just a theory with torsion, but an empirically equivalent to GR theory with torsion. They call it teleparallel gravity. They give you a very particular version of teleparallel gravity, where they write down a connection with torsion, metric compatible connection with torsion, and then they rewrite all of the equations of general relativity, and they announce that what they've now done is written general relativity in a flat space-time with a gravitational force. So they make a big interpretive claim. They claim that they've given you a different space-time. Now, if you look closely at the theory, you realize that the role that the connection with torsion plays is nothing like the role that a connection plays in relativity. It doesn't have any of the right connections to the symmetry groups of the dynamics, because in fact all they've done is permute exactly GR. So the matter fields all sort of sit and do exactly what they were doing before. But they've taken it, and I think this is an instance of mathematical fetishism, right? They've taken it that because they decided to lay down a particular geometrical space-time structure, it comes with an interpretation built in. That's the kind of thing that's the kind of thing that originally made me think this way of thinking was useful to understand what's wrong with a certain strain of theorizing.
So it's kind of getting late, kind of warm. I don't know if I can really ask a question that's only going to take a minute. So we didn't really talk so much. Well, I think everybody else.
Come up here.
Can I have a little indulgence? We didn't really talk a lot about the last part of the talk, really, and I wanted to just have a little discussion about that.
Sure.
But you started saying lots of really interesting things about non-commutative geometry, and then I started thinking through, and then said another one like that. So could you wind back a bit?
Sure.
There's a slide. The next one forward, yeah. So I guess my question is, could you just talk that one through again? And maybe I'll ask something after that.
Okay, so I guess here is the thought. Suppose you were just committed to your theory being the theory on the table being a non-commutative theory represented on the manifold, right? There's just no way to make that look like, you can't write that in a generally covariant form, in part because you just can't, one of the fundamental objects of the theory, the theta matrix, just can only be written in certain coordinates. And literally, I have.
You take the tetra associated with
Mm-hmm.
those coordinates, multiply it, and define this object to be a fixed tensor of your theory. Now it's a tensor. Now you can write it in any other coordinates.
I think the idea is you don't get back the.
I think by definition you get the same.
Correct. Well, yeah. So this.
It's going to be a tensor, right?
It's going to be a tensor, but is it?
A tensor.
But
It's not going to do the right thing in the action.
Yeah, exactly. So it's not going to. The theta matrix doesn't behave like a tensor.
It behaves as a tensor. It is a tensor. It has to be defined as a tensor. It's just.
So I struggle with this too, but that they say no.
No, the point is that it violates the spirit of relativity in having a fixed tensor, non-dynamical tensor into your theory. Anything that you write could be.
Well, hang on. If it's just a fixed tensor in the sense that the Minkowski metric's a fixed tensor, that's rather different. You're thinking, but
there is no global Minkowski metric that you can put in space-time.
what? With,
You cannot put a flat metric in space-time. That is not the metric of space-time.
oh, yeah, but you can model a flat metric. That doesn't violate. That violates the spirit of
But it's not the metric. It's not the thing that will control the behavior of particles.
In our actual world, no.
In our actual world, right.
But when one theorizes about special relativity, it makes perfect sense to talk about a general covariant formulation of special relativity.
You can put the metric there. Now, the question is whether it plays a role in controlling the behavior of other things.
Yeah. No, sure. But I think.
But here, I think the proposal of this theory would be to have this fixed tensor.
Yeah, so I think the theory you end up with if you try and do that is not the theory that you get that these people are trying to write down on the manifold. The theta matrix just does not behave like that. I admit that I find this. The reason I'm flagging it is because if you're used to thinking about classical spacetime theories, it's hard to get your head around how it even looks mathematically. But you don't. if you decide on transformation properties for theta mu nu, which you can do, I can just announce that I think it transforms like a tensor. I think it, but you're not going to get out all of the same consequences that you do when you do this very specific thing, which is what you do effectively to coordinate transform. Here's conceptually what you're doing. If you want to coordinate transform in this non-fundamental representation, you have to kind of think of yourself as translating back into the fundamental representation, coordinate transforming there and then mapping back. And you can't get a geometrical object that reproduces the effect of that coordinate transformation. You got
Because body transformations are not symmetries of this period.
Yeah.
General diffeomorphism is not the same.
Yeah.
It's not general diffeomorphism bias. That's
yeah.
That's why if you hit a space, it transforms properly under this
Yeah. Exactly.
twisted diffeomorphism.
Yeah.
Under non-diffeomorphism.
the fixed tensor that you fix as providing the structure would different under diffeomorphism.
Yes.
Okay, let's get back to Nick.
No, that was. Did you want to? I don't know. So there was another point at the talk where you talked about some Weyl star, and I sort of thought about using that. Well, you can, use this as a sort of wedge to drive between the algebra and the commutative geometry, and argue that it's just representative. We should take the algebra seriously as representing the fundamental degrees of freedom structure of the theory, and the fact that Weyl star in this representation doesn't see the sort of point structure of these fields. There's a reason to think about that. Were you making the point, or do you think it's possible that this point about the failure of general covariance is another way of sort of driving a wedge between the algebra and the commutative representation? Really is showing this stuff in the commutative. We shouldn't do commutative representation.
Yeah.
Sort of, there's more than a sort of representation. We're trying to think about what's the fundamental ontology.
Yeah. So I think that's So that seems. Yeah, so I was sort of thinking about it in the converse way, which is that how do you understand the idea of a theory that can't be written in a generally covariant form? You've got to be thinking that the trouble is that, in a sense, what you've done, every time you write this theory down in this, in the commutative representation, I don't know what the right language is here, but the commutative representation, you're just representing, you're literally producing a, in some ways accurate, in other ways misleading representation of something that cannot be, whose symmetry properties cannot be fully expressed on the normal manifold. That's how I was thinking. Yeah, so I was sort of thinking of it the other way around, which is that, the fact that there's a wedge explains how you could have a theory that looks like this, which doesn't seem to make any sense from the normal way of thinking about space-time theories. But
so just one quick comment. There are other examples where this geometry in algebra picture breaks down. Like, for example, if you have string theory, there is non-associative background, or even if you have monopoles, magnetic monopoles, you have some non-associative field. And in that case, you can't construct a Hilbert space which will be also possible in the commercial context.
Danielle, do you have a comment on that?
Can I take the representation that Weyl star product as totally equivalent to the non-Weyl star? If I can, then it looks just like a scalar field theory of flat space with two extra background structures, which will explain directly why you have different all background structures with a complete tensor. Is a tensor that's fixed values, so that answer obviously has different values. And then with the last phase of method, also there's different values because they're not written like a number. I don't see any special conceptual issue with this, because in fact it's exactly what you can do on the scalar fields on flat space with the external magnetic field. And that is no issue if they're different values in the standard sense.
Good.
The standard model extension is an example of a theory that has this feature.
Good.
Extra fixed
So I'm really open to the idea that I may have misunderstood something that's going on here, because I do find it deeply, deeply puzzling. So there are two things. Maybe we should. There's two things you could mean by breaking diffeomorphism invariance. I mean, just introducing a non-dynamical geometrical structure is, I suppose, as a philosopher, I wouldn't normally think of that as breaking diffeomorphism. I mean, I was thinking of special relativity as a perfectly diffeomorphism invariant theory. Like, just any theory that's written in geometrical terms, I was thinking of that as expressible in any coordinate systems. Introducing privileged coordinate systems, I wasn't taking it to automatically break diffeomorphism invariance in the sense that I took it to be being broken here. Now, maybe I'm wrong about this, and there are definitely people in this audience that can help me with this, but what I think is going on here is that you can represent this theory in a particular set of coordinates on the manifold, but you cannot represent this theory by any theory written in the language of differential geometry on the manifold. So the structure described by the Moyal star isn't expressible as a kosher commutative geometrical entity. It would be a deeper sense of different. Now maybe that's not what's going on here. Maybe it really just is that the theta matrix is just like the Minkowski metric and is just introduces privileged coordinate systems in that sense, in which case this is much more familiar. But on my understanding, that's not what's going on. But I mean, my understanding is partly predicated on stuff Nick said and then seeing that backed up elsewhere in the literature. So I'm not blaming Nick.
Yeah, just kind of my answer to Daniel. So one thing is what Pseudo said. So there really are non-commutative structures where you just can't reconstruct in this way at all. So those seem sort of interesting. And also the point I was making a little bit earlier about the Moyal star. I mean, if that's really how two fields are supposed to be taken together, so I sort of then have feelings that you're not seeing the point structure of the fields, and then that suggests there's not really a sort of commutative manifold there. But I do have to say I have those feelings are sometimes stronger than other times. And I understand the kind of fiction you can, but it's not clear cut that that's not the right thing to say.
So I think that there just isn't a representation theorem between this theory treating that theta as any kind of object with well-defined transformation theorems and the non-commutative theory. I think maybe that's so you might wonder about the relationship between those two things, but they're not, they don't map in the right kinds of ways, right? I think. Yeah. So I think there isn't. So I think that there isn't. I'm pretty sure that there isn't. Yeah. 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 So I think it's worse than that. I think there isn't a full equivalence. This is a kind of way, but Nick's looking doubtful. So I think I don't know.
But only on fixed space.
No.
That's specific here.
Right.
That's specific.
So not a theory. Yeah.
Remember, you can write it as a theorem of that space with this standard form, and everything translates into a complicated number of derivatives.
And that's, the action has powers of the theta movements, like the
There are some problems, but I'm saying that this specific example, but this specific theory can actually be realized physically in standard Minkowski space. So it's hard to draw in conceptual. So this specific example, the general
So this is as a non-commutative field theory is perfectly built and you can take, but I guess if you try to then use this as a non-commutative gravity theory, it's more complicated because now you're redefining Lie derivatives and things like this.
Exactly. So any extension of this in which you try to make it generally covariant, but also removing the flat Minkowski space which is there, would be a totally different story. Exactly. That's when you try to make it generally covariant. You have to go first and you realize that require classic rethinking of these space-time structures in order to make it generally valid. Because in itself is not a structure to make it generally valid. In fact, it's a standard scale more and more of the power.
Okay, so we should wrap up the discussion. I don't know. Did you want to say something?
No, that's very helpful. Let's chat about it.
Okay.
I have a question. That I needed to ask for a while. It's a question about your question.
To me?
Yes, it's a question about your question. I
I
want to understand, I want to understand this. If we all believe that GR should emerge from quantum gravity, how do you make this transition between the functionalist and substantialist point of view and make the deduction? What's left of this emergence if you take this to the point?
That's an excellent question. I think I have some things to say about it, but maybe we should start to do that over dinner, if you agree. So please join me in thanking Eleanor once again.